Hi. Hi, everyone. I'm Titouan. Yeah, that's why he didn't want to try. I'm going to talk about lightning-fast routing engine in TypeScript. So that's a lot of stuff to explain. We'll see about that. First things first, I'm an engineer at Symfony. Symfony, PHP framework, you probably heard of it, perhaps not, it's fine. We can discuss it afterwards. And I'm here for Buzz.io. Buzz.io is an app I made as a personal side project, and I implemented inside a routing engine. So routing engine is going from point A to point B as fast as possible. We'll discuss that a bit. So at Symfony, usual classical thing, we hire a lot. So if you want to discuss that as well, I'm up for that. I'm French, by the way, so if you have specific wrong pronunciation for stuff, don't hesitate to raise your hand and ask. I'm perfectly fine for that. So we're going to talk about a lot of different things, which are all related, I promise, but which are quite different at the same time. So the first thing will be to try to define a goal for this presentation, and then we will try to discuss what's the routing problem and how I implemented a fix, well, a solution of it, which is called the Connectionscan algorithm, into a project I had. So what's the goal? What's the specific goal we have? The goal is to let users find the quickest way from point A to point B in terms of coordinates as fast as possible. So to go, I don't know, from LinkedIn headquarters, to go from Golden Gate Bridge to LinkedIn headquarters as fast as possible, living at 6:55, for instance. So this is something we usually do use every day, like on Google Maps and stuff like that, but it's actually a bit more difficult than I thought to implement. So this problem, which is a real-world problem, is actually a routing problem. So it means it's something we know as mathematicians, and I'm pretty sure you like mathematics, and if you don't, that's a shame, because it's really nice. In mathematics, we know this problem with another name, and this other name is, I'm going to change, is the shortest path problem. So going from point A to point B as fast as possible is called the shortest path problem. And this problem, which is a mathematical problem, is based on something called graphs. Does everyone know about graphs, or do you know what's a graph? A graph, not a chart, a graph in mathematical terms. I'm going to introduce it, so it's fine if you don't. Graphs were invented pretty much 300 years ago, so it's a while. By someone I'm not able to pronounce the name in English, sorry. Euler, okay, nice. I wasn't sure about that, so I didn't try. It's a really powerful model which is used a lot across the field of computer science, from AI to blockchain to compilers and a lot of other fields. And it's used in what's called the routing problems. So there are a lot of routing problems, and they are all based on what's called graphs. So they can be either oriented or not, meaning that each node, each circle has a link to other nodes, and these links can be oriented or not. And when they are, you add an arrow to them, and it means you can only go in one direction through them. So it's quite simple to understand, but it's actually a really powerful model on which you can add and implement algorithms to find, for instance, the shortest path, or to clusterize data into, I hope it won't drop, artificial intelligence and a lot of other things. You can also add weights on these graphs, meaning you can add a value on each edge, and if you add this value, it can mean a lot of different things. In our case, we will have nodes, so for instance, A and C would be bus stops, and the value of each edge would be the time took by the bus to go from point A to point C. So this model is really important and really powerful because it has a lot of implications. So it's been a while since we think about it, as I said, 300 years ago. But mostly we thought about how to implement powerful graph algorithms when we invented IT and computer science. So the first really important algorithm for shortest path problem is called Dijkstra algorithm. The next one, it was invented in '56. The next one is called the Bellman-Ford algorithm. It's powerful because it handles negative weights, whereas Dijkstra doesn't. And then the A-star algorithm is also famous because it's an extension of Dijkstra, which is much better in real life, even if it has the same complexity. And it's the most used today because it targets the optimal solution much faster. So these are pretty much all the algorithms, basic algorithms we have to solve SPP, so shortest path problem. But the thing is, it's O n log n, so its complexity is pretty much the same as a sorting algorithm, which is nice, but it's quite generic as a problem. It can solve a lot of different tools. In my specific case, I had constraints, an additional constraint. Public transports are not classical transports. You have timetables. So when you have timetables, you have a new constraint in which you may be able to find a better complexity to solve this specific issue. And that's what I looked for, and I found Connectionscan algorithm. So the Connectionscan algorithm is an algorithm developed specifically for timetables, for SPP with timetables. It was developed in 2012, so really, really recent, in Germany by a lot of different universities. And it targets only SPP with timetables. Its overall complexity is quite the same as Dijkstra, so we may think, okay, it's not really useful. But what's interesting is that there is the possibility to have a preparation step, which is C log C, but then the query itself is linear, which is really great because it means you can have a huge network, a burst network, for instance, and it will still be quite efficient, even if you add a lot of stops, for instance. So it's really important. So the first thing we have to say to describe this algorithm, that's kind of the aim of the presentation a bit, is to talk about what's a connection. So a connection is another representation of the graph. So you have a graph from node A to node C. But instead of representing the graph with nodes on edges, you will represent each connection with the departing time and the arrival time. So for instance, here you would go from a node A, so a bus stop A, to a bus stop B, from 742 to 745. This is a connection, the object itself. And then you would list all these connections into a single array instead of having a graph. This is really useful because then you have a really simple data structure that you can loop on. And using this data structure, you can have a linear complexity. That's what we're going to see today. So instead of storing the graph, you store connections. OK, so for the implementation. So first things, do you have questions yet? Do you have, is there a weird, yeah. Is it, yeah. Sorry? Real-time data, you mean?
Well, in the real life, arrival time can be early or late.
Yeah.
So do you allow for some kind of...
Absolutely. That's one of the things. OK, so that's a really interesting point. I guess it would be easier to answer it afterwards because next in the implementation I will talk about this kind of stuff. If you have specific questions about the concepts, it's easier. But thanks for the question. I'm going to answer it afterwards. OK? Everyone got the concept. Nice. Then, for the implementation, I use TypeScript. I'm pretty much sure everyone heard of TypeScript. TypeScript is really nice, in my opinion, for a lot of reasons. We can talk about that later. But one of the main reasons is that it's easy to use dependency injection on such patterns that let you decouple your code a lot. So I used it to build a resolver, so implementing the algorithm, and then build all the other things needed around it. So I'm going to talk a bit about that at the end of the presentation. If you see some code that is kind of weird for JavaScript, that's because it's TypeScript. So first things first, as I said, in the CSA, so connection scan algorithm, the first thing you do is to prepare something. So actually, you prepare the list of all the connections, usually for the day, for instance, and you prepare these connections and order it. That's why it's the same complexity as the sorting algorithm, the Oise log C. Then you have a huge list, probably huge list, of connections. And using this connection, you iterate over all the connections, and that's where you will have Oise. The first thing you have to do is to prepare all the data in memory. So what's going to happen is that, let's say, for instance, you want to go from point node A to node F. What's going to happen is that you will, as in Dijkstra, calculate, compute every single earliest arrival path to every other node. So you will compute at the same time every shortest path from A to B, from A to C, from A to E, from A to F, etc., etc. You will compute this in one single loop, and then using where you want to go, you know where you want to go in the problem, you will backtrack this list to find how to go to this specific point the quickest way. So the first thing you have to know to store is the list of the connections, the quickest connections to every node. And you can also, that's what I did because it's useful, have an independent array for the same data, but only for the times, arrival times, just to ease the comparisons. So let's take an example. Here we have a list of connections. We have a list of connections on the right. And for each connection, we are going to just have a list of small conditions to check whether this connection is the fastest way to arrive to this point. The first thing we have to check is that we never arrived, if we never arrived to a connection at this point, it means this connection, as it's ordered by arriving time, we aren't going to arrive to this specific connection in the future. So for instance, if we leave from A and we want to go from to F, and we go through this connection, G was never, we never went to G using the connections we iterated over earlier. So this connection doesn't apply to this problem, this query. Then we are going to try to find whether the new connections we are currently analyzing is better or not. That's the connections we had earlier. So we are looping over each connection, and when we reach D, for instance, well, D, this one is cancelled, but if we reach E or E, we are going to see that this one is better than this one, so we are going to keep this one. The C to E is better to go to E than the B to E. And then we are going to have, if there was already a connection arriving, oh, I missed. Yeah, I mixed the two. Yeah, well, but it's written on the command, so it's fine. And then using only these three conditions, we are sure that each time we reach a connection, we will add it to the list of best connections. And we are sure, definitely, because it's ordered by arrival time, that we are not going to find something better in the future. So it means we can add this to the list. And the whole algorithm is in this loop, which is kind of elegant, in my opinion, because it's really tiny and it works really well. And then using this list that we have, so for instance, we would get the best way to go to B is to go through A, because it's the fastest way. To go to C, it's through B, to D, it's through B, etc., etc. And using this list, if we want to go to E, for instance, we're just gonna go from E, so iterate over the list, go from E, then we are the best way to go to E is to go from C, so we are gonna check where the best way to go to C is. So we are gonna be E, C, C, B, and B, A, and we are gonna have the result that A, B, C, E is the best way to go. So it's actually quite simple as a way to build such routing engine, but what I like about this algorithm is that it's mostly based on its data structure. So I feel like it's a nice interesting way to say that if you change the data structure, it can change a lot the complexity on the algorithm itself and improve it, hopefully. Okay, so now we have the best way to go from a node to another node. But as we said, from a node to another node, usually nodes will be bus stops. What if we want to walk in between stops or just before the first stop and at the end of the last one? I would like to have multiple results to be able to choose from them. All this stuff is where TypeScript or JavaScript comes in, because we are going to parallelize a lot of things. So the first thing we have to keep in mind is to be async, of course. The first thing is I'm using what's called OSRM, which is an open source project based on OpenStreetMap data, which is able to compute locally every single thing that Google Maps is able to do on a global scale. Well, it's able to compute route, not to translate an address into a coordinates, but it's enough for my usage. So what we are going to use is this for the walks, and the global architecture can be summarized as this. So we prepare in advance all the connections on the walls, as I said, and then we are able, with TypeScript, to parallelize all the walks we can do from the starting point as the coordinates to the nearest bus stops, and the walks we can do from a bus stop to the end of the journey. So we parallelize all this. I personally chose, it depends on the city the application is working in, but I chose to find the 5 closest. I create, using OSRM, the walks, and then using the TypeScript async features, I'm able to run the algorithm a lot of times in parallel, which means as they are independent one from each other, it's really, really fast. Really fast, like in 100 milliseconds, I'm able to give an answer usually, and at max it's 150. So it's the network is not that big, but it's quite big for the biggest city. So it's really interesting algorithm for that. Thanks.
Question time.
So you had one.
Are you going to post the slides? Because that was a really good presentation. Is it 150 milliseconds on average local, or is that your average?
Including network. So it's in production. It's, yeah. Yeah, that answers the question, I guess.
You're going to post the slides, right?
Yeah, I'm going to do that, yeah. Yeah, you had one, right? About errors.
I asked there's uncertainty.
Yeah, yeah. So about uncertainty, yeah. So what's great about this algorithm compared to Dijkstra's one, for instance? So Dijkstra's algorithm is based on a kind of static graph. So it works with the data structure of a graph, and then it iterates over the nodes to compute the best, kind of the same idea, but it's based on the graph. What's difficult is that weights, as in a dynamic real situation, can change. And in Dijkstra, it's quite difficult to integrate this change. Whereas when you have a single map of data, you could just iterate over the data that's changing. And usually, as it's ordered, you are well, I didn't do that because I was kind of lazy, but you could technically map the data to the right time and be able to not even have a loop for that. You know what I mean? You could just find the connections by the arrival time, and if the arrival time change, then you just iterate over all the connections that have this specific arrival time and update them. So it's actually quite easy to do inside the algorithm itself because the data is already made for it. We can discuss it if you have more questions.
Any other questions?
Whew, that's a dark.
With OpenStreetMaps, do you use it for crisis camps?
I'm not able to hear you much.
What are some of the other issues or things you think using the OpenStreetMaps code was use it for the crisis camps to kind of dig people out and figure out routing for Haiti and others. What are some of the things you'd like to see inside of that tooling, or some other tooling outside of it that needs to be a bit better routing, physical routing, open source routing?
I think the biggest challenge is data. And that's why my application is here. That's because I implemented the specific problem for a specific region in which I have the data. But you cannot scale this kind, it's difficult to scale this kind of thing because the data is not universal and not well organized. And one of the things Google tried to launch, and it succeeds, kind of, is Google Transfer File System, which is a format that is made to transfer this specific kind of data for buses. But when you don't have the data, you are not able to do any algorithm. So
Even the Nextbus API and some stuff around Cover1.org that's locally in California isn't actually accurate. It's a real issue. Nextbus API around the country, and at least in the United States, isn't really that accurate. And so that's an issue. That's what I was asking.
Yeah.
They're obfuscating a lot more for security reasons, but it makes it hard to get buses on time.
Yeah.
And the update period from the actual sensors on the buses are kind of messy too.
what, the algorithm I use is actually used by CityMapper as well. If you heard of CityMapper, I guess, perhaps. CityMapper is kind of a concurrent, but they are not interested in small cities like I do. So yeah, I don't know. But what they do is they have way more customers than I do, well, users than me. And so they implemented a way to track the location of users and to detect from the location of users inside the bus whether the data is right or not, and learn from it into a machine learning algorithm to predict stuff. So that could be an idea. Otherwise, you could just put Raspberry Pis into buses. Would work as well, but
Google Maps, Android senses for traffic and mapping, Google Mapping, they use that as a way of validating the data from phones. So you got to start paying for it from
yeah, Google does that with traffic, and CityMapper could. Yeah, okay. I'm not sure to understand everything because it's quite far, but yeah, we can discuss it.
Yeah, it's getting a little into the weeds. Are there any other questions? Thank you, Titouan.
Thanks for the name.